Today, we're going to talk about properties of quadratic functions. We're going to start diving in specifically to these quadratic functions. Before we get started today, I do want to do a little recap of where we've been in the curriculum. Guys, one of our first lessons was just about functions. What is a function? Identifying a function that their x's do not repeat, that they pass a vertical line test. From there, we dove deeper into specific types of functions, starting with linear. And we did so much with linear. We went back through slope-intercept form and graphing linear functions. We talked about linear systems, graphing two lines together and solving those types of systems, linear inequalities. So we really focused on linear. We also took a moment and we looked at exponential functions. If you remember, those looked like rocket ships, and we talked about exponential growth and decay. And then most recently, we took time talking about polynomials, and we were identifying polynomials. We were starting to simplify polynomials, multiply them, add, subtract them, those types of things. And one type of polynomial is the quadratic. The quadratic has an x squared. It has that squared as its highest degree. And so we are going to focus now on a specific type of function called quadratics. So that's where we've been and why we've kind of gone in this order. We started with functions. We focused then on linear. We focused on exponential. I gave you some groundwork of where we're going for quadratic. So let's dive in today and look at quadratic functions specifically. So a quadratic function is a function with a degree of 2, and that means that the highest exponent on our variable is 2. The next line here, the simplest quadratic function, or it could be called just like the parent function without any extra coefficients or extra terms, is y equals x squared. So you can see that 2 there to make it a quadratic. And it graphs a curve called a parabola. Now, a parabola is going to be that soft U shape that you see every day. If you took a piece of string or yarn and you let it loose, it would make a U shape and be very curved as gravity pulled down on it. So on the right here, I've given us a graph where we can create one of these quadratic functions, just the basic y equals x squared. So let's make a table of values. I'm going to make a list over here of x values. I will evaluate in our function and see what our y value is. So let's start with like -3, -2, -1, 0, 1, 2, and 3. These are just random x values that I'm choosing, but it is going to create our basic shape and fit on our graph. So if I plug in -3, now be careful when you are squaring negatives, when we're plugging it in for x here, it's getting replaced and it's in parentheses. So I want -3 times -3, which is +9. So I will have an ordered pair -3, 9. I'm going to come over here to -3 and go up. Oop, 9 is going to be off our graph a little bit, but let's go ahead and plot it there. Doing the same thing with -2, when I put parentheses around it and square it, I get a +4. A negative times a negative is a positive, right? So -2, +4, graphing right there. When I plug in -1 squared is +1. So I'm going to go and plot -1, 1. If I plug in 0, 0 squared is still 0. So we are sitting right there at the origin. 1 squared is +1. So you can see when I plug these in, 2 squared is going to give me 4. I'm getting a parabola. I'm getting this U shape, and it's also symmetric. 3, 9. So here I have this U shape as I connect my dots, keeping that nice curve there. It looks like a U, or it's called a parabola. So there is our most basic quadratic function there. When we were studying functions, we also talked about function transformations. So on your notes, it says, recall that changing the parameters of a parent function produces transformations in its graph. Not every parabola is going to sit right at the origin. It might be up or down or left or right. So let's review that here really quick. The first one here, y equals x plus k. If I add a value at the end, it's going to shift my graph up that many units. So I'm going to write up k number of units. So if there's a 3 there, it's going to go up 3. If it's a 7, it's going to go up 7. The second one, y equals x minus k. So same idea, except we're subtracting. So it's going to move down k units. The third one, y equals, and we have parentheses around x minus h. So if you have subtracting inside, this moves it side to side, but it is opposite the direction that you would expect. So it's actually going to move to the right h number of units. And the last one, and then we're going to look at these examples. Y equals the quantity of x plus h. When you're adding inside parentheses there, you're going to move left h units. All right, so let's take those 4 possible transformations and apply it to our examples 1, 2, and 3 here. Example number 1, y equals x squared plus 2. We've got that plus 2 there. At the end is going to shift it up 2. So we're still talking about a plane parabola, but by adding 2 at the end, now it is shifted up the y-axis 2 places. I'm going to just sketch that, making 2 tick marks there and sketching my U-shaped parabola. Example number 2, y equals the quantity of x minus 1 squared. The squared right there is just making that parabola shape, minus 3. So we've got a subtraction inside is going to move us right 1 unit. And then we've got minus 3 at the end is going to shift us down. So let me go to this little graph here. I want to go to the right 1 and down 1, 2, 3. This is where my origin would be moved to, and I've got a nice happy parabola right there. So it got shifted right 1, down 3. The last one here, and then we'll look at other changes on our functions. Y equals the quantity of x plus 2 squared. Again, the squared's making that parabola shape, plus 1. So inside the parentheses, we've got adding 2. That's going to shift us left. Plus 1 at the end is going to shift us up. So I need to go to the left 2 spaces, and up 1 is where I now sit with my parabola and making my U shape. It would look something like that. These are obviously not precise graphs. We're just sketching. So if I was looking at multiple choice questions and I had different graphs, I could probably eliminate and pick them very quickly without having to exactly graph them. All right, let's go back to those parameters. The next one we have is y equals negative x. If you have a negative in front, this one's my favorite, it flips or reflects your graph upside down. It reflects it over the x-axis. So let me write both of those. We're going to reflect over x, over the x-axis, or I like to call it just upside down because a lot of students understand that. Okay. Next one, y equals a times x. So if a was a coefficient and a is greater than 1, it's 1.5, it's 2, it's 8, it's 72, whatever that is. When you have a coefficient in front of your x value that's greater than 1, this is going to stretch it vertically or it's going to make it skinny. So a vertical stretch, or if you want to call it skinny, that's a way I know. I call it skinny. The last one, y equals a times x. Again, another coefficient, but if your coefficient is between 0 and 1, if it's a fraction, if it's a decimal, this is going to cause a vertical compression. So if I think about taking Play-Doh in my hand and I squish it, what happens? It gets wider on the sides. So this is called a compression, or it's going to look wider. So let's look at some examples. The first one, y equals negative x squared. We've got a negative in front, but we're still just dealing with x squared. The function we're working with is x squared, this quadratic that makes a parabola, but we've thrown a negative in front. So it just gets flipped across the x-axis. It's now a frowny face. It's an upside down U. The second one, y equals negative 1/4 x squared. X squared is making our parabola shape. What else do we have going on? Oh, we've got a negative, so it's upside down. And the 1/4 is going to compress it. That's a fraction. So it's going to be a wide upside down U shape. So let's sketch that. I'm going to make it extra wide. So when I look at my notes, I remember a fraction or decimal is going to make it wide. Let me even add that here. Wide, and it was upside down because of this negative. The last one, y equals 5x squared. So we've got a 5 coefficient. X squared is still making our parabola U-shaped. The 5 is going to make it skinny or stretch it vertically. So we're still sitting at the origin. It's still a happy U-shape. We didn't flip it upside down with a negative, but it is skinny. If I was to take my yarn and put my hands really close together, it would be a very steep, skinny parabola. So on Delta Math, you have some problems where you're going to match graphs with their A value. You do have to click and drag a little bit, so play around with that. Let me know if you need help manipulating that, but match each of the following graphs to the appropriate A value. So the coefficient in front, would it be, if it's greater than 1, it's going to make it skinnier. Or if it's a fraction or decimal, it's going to make it wider. So let's look at this example. Our A values are negative 0.25, a 4, and a 1. So the 1, letter C here, A equals 1, that's our normal parabola. So just happy as can be. Now, all of these have been shifted a little bit. They're not sitting at the origin. Don't let that fool you. Just think about the shape. So this first one, this first graph is actually just a happy parabola. It's not too fat. It's not too skinny. It's just normal. Now, A, we've got the negative, so we are upside down. That's a big giveaway. But it's also a decimal, so look for something that is wide. And then for B, the 4, an A value, coefficient value of 4 on our parabola is going to make it skinny. So hopefully you can decipher between these. We obviously only have one parabola. That is upside down, and that's the second one. So I'm going to label that one A, and that leaves the last graph to be labeled with B with an A value of 4, making it really skinny. Let me label these for our notes here. Graph A was 0.25. We got that upside down and wide. And then C, our A value was 1. So on Delta Math, you're going to click and drag a little bit so to make those line up. All right, getting a little bit deeper into our quadratic function, the standard form for an entire quadratic function, y equals ax squared plus bx plus c, where a, b, and c are all numbers. We would replace those with coefficients or term values, constants. So the a, b, and c would be replaced with numbers. I've got two graphs here to the side so we can look at a parabola and identify some key features. The first thing is when our A value is positive. So I'm filling in this first blank here. When that A value is positive, our parabola opens upward, or you have a nice, happy, smiley face. We were talking about this just a minute ago with our transformations. If the A is positive, normal parabola. Now the counter example here, when the A value is negative on this other side, the parabola is going to open downward, or it's going to be a frown. And those line up with our examples above. On the left side, happy parabola, the A value for that graph is going to be positive. In our second graph on the right, it's upside down, and so the A value would have to be negative because we got a frown there. Our next blank is the axis of symmetry. Now, the axis of symmetry of the parabola is a vertical line that passes through the vertex. Determine the equation for your axis of symmetry in each parabola above. So I'm going to label it here. You're going to go, wow, that was simple. Your axis of symmetry is straight down the center of the parabola. It's what makes it symmetric. So I'm going to doodle on our graphs up here, those axis of symmetries. I'm going to label 2 as well. Axis of symmetry, I'm doing it in orange. Draw some arrows to those, okay? So for each of our graphs, we are going to determine the equation. Got to have an equal sign for my equation for these axis of symmetries. These are very easy. You're going to start with x equals, and then tell me what number that line is passing through. So this one on the left is x equals 4. It's passing right through that 4 on the right side. our axis of symmetry is going to be x equals 1. It's passing right through positive 1 right there. So add those in as your examples. We wrote the equation for our axis of symmetry, that invisible vertical line that goes right through the center of our parabola. Our next blank, the vertex, is the point at which the minimum or maximum of the function occurs. It's our lowest part or our highest part. So let's determine the coordinates, x and y, of the vertex of each parabola that we've got above, okay? Let's go up here. Let's do those in pink. So I'm going to go down to this very bottom of our parabola. This is our vertex of the left side, and it would serve as a minimum value. It is our low point, right? That ordered pair would be 4, -9. Notice the 4 was also the axis of symmetry value, right? 4, -9 is the vertex of the first parabola example on the left. On the right side, we've got our vertex up here. And because our parabola is upside down, now it's serving as a maximum value. Its ordered pair is going to be 1, 4. Notice the 1 for the x value was also the x value of our axis of symmetry, right? Because the axis of symmetry goes right through the vertex. So 1, 4 is the coordinates for the vertex of our second example. The next blank is x-intercepts. The x-intercepts, also called zeros and roots, is where the graph crosses the x-axis. Determine the coordinates of the x-intercepts in each of the parabolas. So let's do that in light blue. I'm going to go up to the top here. On the left, we've got an x-intercept right there at 1, and we've got another one at 7. Now it said to list the coordinates, so we're going to list 2 sets of x and y. We've got 1, 0, and 7, 0 are our x-intercepts. Go and do the same thing for the second graph. Our x-intercepts, now these can also be called roots, -1 and 3. Write it as an ordered pair, -1, 0, and 3, 0. X-intercepts, also called roots and zeros. Our last blank is y-intercept. Your y-intercept is where your graph crosses the y-axis. Determine the coordinates, x and y, ordered pair, for your y-intercept in each parabola. Let's do that in yellow. So on the left, it is crossing the y-axis at 7. That ordered pair is 0, 7. 0, 7 for that first one is our first y-intercept. In the second graph on the right, let's see, it's crossing right there at 5. So that's 0, 5 is our y-intercept. 0, 5, putting it on our blanks as well. So there's parabolas. You can see for now we're just identifying characteristics of our parabolas, identifying the axis of symmetry, the middle of our parabola, the invisible vertical line that separates our symmetric halves of our parabola, the vertex, which they could also ask you about minimum or maximum, and it means the same thing. You're looking for that vertex point. X-intercepts, which could also be called roots or zeros, and our y-intercepts. So this is getting us started to study quadratics specifically. We're going to actually graph them a lot more. We are going to eventually solve quadratic equations. And so this is amazing groundwork for you, knowing the general quadratic shape of a parabola, your transformations, which should be review, and then, like I said, identifying those characteristics of our parabolas. Guys, let me know if you have any questions. I'll be glad to help, and then I'll see you in class. Hope you have a great day.